A1, A2, all the way up to AN, B1, B2, all the way up to Bn are all real numbers. So Cauchy inequality tells us that A1 times B1 plus A2 times B2 all the way up to AN times Bn quantity square is no larger than the product of the sum of squares, where A1 squared plus A2 squared plus all the way up to AN squared quantity times B1 squared plus B2 squared plus all the way up to Bn squared. And of course, equal sign holds if and only if the numbers are all in proportion. In other words, A1 is equal to lambda times B1, A2 is equal to lambda times B2, all the way up to AN is equal to lambda times Bn for the same lambda. And we're going to first construct two matrices. Matrix A, let's call it A1, A2, all the way up to AN. The second row is B1, B2, all the way up to Bn. Of course, the size of the matrix is 2 rows, n columns, right? 2 by n. We have a matrix B. B is equal to A1, A2, all the way to AN. B1, B2, all the way to Bn, where the size of the matrix is of course n rows, 2 columns, n times 2. Of course, it's multiplicable, right? A multiplied by B. So what is A times B, right? It's going to come out as a 2 by 2 matrix in the end, of course, right? 2. So first element, right? First row times first column. A1 times A1 plus A2 times A2 plus. So in the end, we have a sum of AK squared. K goes from 1 to n, right? First row, second column, right? First row times second column. A1 times B1 plus A2 times B2, right? All the way. So in the end, we have the sum AK times BK. K goes from 1 up to n. Right, second row, first column. Second row times first column. B1 times A1 plus B2 times A2, right? The same thing as this one. So AK, BK, right? Right, suppose it's BK, AK, but I can switch it. AK times BK, right? This is definitely doable. K goes from 1 to n. Then we have second row times second column. B1 times B1 plus B2 times B2, right? So very similar to this one, except we have BK squared. K goes 1 to n, right? Now, the determinant is denoted as 2 bars, right? Determinant of AB. That is equal to this times this minus this times that, right? So sum AK squared, K goes from 1 to n, times sum BK squared, K goes from 1 to n, minus this times that. That's the same thing, right? So this quantity square. So sum AK BK, K goes from 1 to n, quantity square, right? This is almost very close to this part, right? This part, this sum is this part, and this sum is this part, and this part is just this part, right? All we have to show is that this is larger than or equal to 0. Then we're done, right? The same. So also according the same thing equal to according to Cauchy. Cauchy theorem, right? That tells us that to calculate the determinant of a product of 2 matrices, right? As long as the matrix of the left-hand side matrix, the number of rows is the same as the number of the columns of the right-hand side matrix, right? They're both 2. And of course, the number of columns of the first matrix is the same as the number of rows of the second matrix. And at the same time, we know that the number of the columns of the first matrix is greater than or equal to the number of rows, right? N is larger than or equal to 2. If n was equal to 1, then A1, B1 quantity squared, is it smaller than or equal to A1 squared times B1 squared? They're equal. So when n is equal to 1, it's obviously true, it's trivial. So we automatically assume that n is bigger than or equal to 2, right? So that way, Binet-Cauchy theorem can be applied. But right, as long as this one is larger than this one or equal to this one. But if this was smaller than this one, then determinant will be 0. So in this case, it's non-zero. And according to the theorem, that is the sum. The sum I smaller than j, smaller than or equal to n, bigger than or equal to 1. A, row 1, row 2, column I, column j times B. I'll explain what that means. B, row I, row j, column 1, column 2, right? So the meaning of this expression is that, so this part represents the determinant of row 1, row 2 combined with column I, column j of matrix A. For example, right, we only have 2 rows, row 1, row 2 combined with column I, column j. So that's what I mean. For example, column I, column j. Right? So we're looking at AI, AJ, down here, BI, BJ. These 4 elements matrix, its determinant. That's what it means. Right? Same goes for B. So this notation means we're looking at the determinant of the submatrix of matrix B. Right? Call row I, row j. Row I, row j. Row I, row j. Right, somewhere here. Column 1, column 2. Column 1, column 2. Right? So we're looking at somewhere down here, AI, BI, AJ, BJ, looking at this 4-element submatrix, its determinant. And multiply together, then we do the summation. Right? So every possible combination of I and j, where I is less than j, in between 1 and n, right? For example, you have 2 and 3, right? 1, 2, 2, 3, 2, 3, 1, 2. That's one possibility. You have 6, 9, right? 1, 2, 6, 9, 6, 9, 1, 2. You have 1, 2, 10, 20, 10, 20, 1, 2. All those different combinations, you just add them up. As long as this number is smaller than that number. So basically that would equal to, like I said, that would equal to sum I, j less than in. This determinant times that determinant. Like I said, this determinant is nothing but AI, AJ. AI, AJ. BI, BJ. BI, BJ. Right, that determinant is nothing but I, row I. AI, BI. AI, BI. Row J. AJ, BJ. AJ, BJ. So that should give me aj times ai times bj minus aj times bi times ai minus bj times minus bi times aj. Right, then we do the summation. So that is just equal to I less than j less than n bracket ai times bj minus aj times bi. Then we have ai times bj same as this one, minus bi times aj same as this one. So essentially this and that are the same, right? Just square it. So again, like I said, determinant AB is equal to this part minus that part, which is also equal to this part, but this part is a sum of squares. So definitely larger than or equal to 0. Right? Of course, real numbers, right? So in other words, when do they equal? When is it equal to 0? It equals 0 if and only if every term is equal to 0, right? Every ai times b, so larger than or equal to 0. Right? ai bj is equal minus this is equal to 0, is equal to aj times bi. In other words, ai over bi is equal to aj over bj. Of course, we have to require every bi bj not equal to 0, right? That way we can perform division. That way we're safe. And so in other words, according to this logic, A1 over B1 should equal to A2 over B2 all the way equal to AN over BN, right? That's when equal sign holds. In other words, they're all in proportion and their ratio, let's denote it as lambda, right? So A1 is equal to lambda times B1. A2 is equal to lambda times B2 all the way. AN is equal to lambda times BN. That's when equal sign happens, right? So what happens if one of them is 0? Let's call it BR is equal to 0, fixed R, right? So that means this part, this term, right? Well, so I replaced with R, so AR times BJ. J may be changing. BJ minus AJ times BR quantity squared, right? Okay, BR is equal to 0, so that means that is equal to AR BJ quantity squared, right? Of course, still bigger than or equal to 0. Right, still true. The question is, when will equal sign hold? Right, of course, if and only if this term is equal to 0. But not just one term, because even though R is fixed, J may be still changing, right? Here the requirement is that J is bigger than I. So in that case, J is bigger than R, right? We have many, many terms as long as J is bigger than R. As long as every such term is 0, then we have equal sign, right? The other terms, there is BI that's non-zero, then for the same reason, right? So the other terms are safe. So these terms, right? What happens to these terms? Right, so like I said, equal sign happens only if and only if this term is equal to 0. So when does this term equal to 0? Like I said, only BR is equal to 0. The other BJ are non-zero. So we can only require AR to be 0. Okay? AR. Right, R is fixed. So that AR times, for example, BR plus 1, right, quantity square is equal to 0. And AR times BR plus 2, right, quantity square is equal to 0. Right? So that every such term is equal to 0. And for the other terms, right, for the other terms, they equal to 0 when numbers are in proportion. So the other terms are safe. Right? The same old method. So that means overall, it's always true, right? No matter if all the b's are non-zero, or if one of them is 0, right? Still doesn't matter. Still true. Still true. Like I said, AR is equal to 0. At the same time, BR is also equal to 0. Still doesn't matter because I still have this relation, right? This proportion means 0 is equal to lambda times 0. Is it true? Yes. Always true, right? Right, for the same, still true. Right, so no matter what, no matter we have non-zero b's or one of them is 0, two of them is 0, right? Doesn't matter, always true.